My name is Kareem, and my research concerns dual-phase steels. I put an image of such a steel here. It's a ductile ferrite matrix containing hard martensite inclusions, and it's already very often used in the automotive industry for its good strength, ductility, compromise. What I have mostly done up to now is to model the plasticity of the steel, so I'll say a few words about it, and I'm beginning to work on damage and fracture toughness. And this is because the ultimate goal of my work is to predict and improve the fracture toughness for automotive applications. And it's important to improve this property for several reasons, such as to avoid the propagation of a crack that has appeared during cutting when undergoing subsequent forming operations. And another reason is for structural components which we want to resist cracking during an impact. So quickly for the context, the second slide. I put an image here, the same one as the one on my title slide. It shows the microstructure of a traditional dual-phase steel. And by that I mean with ICAPS inclusions. On the right we have the heat treatment to obtain this microstructure. It is the heat in the intercritical range followed by a quenching. However, it's possible to change the morphology of the martensite inclusions by applying modified heat treatment with two steps. The first one in the full austenitic zone, followed by a second one in the intercritical zone. And that leads to a fibrous morphology. But as a first quick result, I've done a 3D microstructure characterization of such a steel using a serial section procedure. And it gave us information that the martensite inclusions aren't fibrous, as we thought, looking at the microstructure in 2D, but rather ladled platelets. And it's important to me to know the morphology, because it's a parameter I want to study. And why we want to study this parameter is because we think it has a very important role to play on fracture toughness. And why we think that, we'll come up with on the second slide of the fracture toughness. Foremost, there are not many studies on the fracture toughness of DP steels, and when there are values, we would often like them to be a bit higher. They rarely exceed the 200 kilojoules per square meter, like shown in this graph, that gives the J1C as a function of martensite volume fraction. However, amazingly enough, there are some DP steels with the fracture toughness measured recently at the UCL that far exceed the common values. It's those steels here. And the big difference of those steels is that they exhibit a plate-like microstructure. That's why I'm interested in morphology and why I'm working on those steels. Why it's so high and if it's can be improved is something we do not know yet, that we would therefore like to figure out. Another important information about those steels, those measures here have been taken on thick sheets of about 10 millimeters thickness using the compliance method, whereas I'm more focused on thin sheets, since it is thin sheets that are of interest for the automotive industry. And in that case, there also exists a method to quantify the resistance to the propagation of a crack called the essential work of fracture, EWF method, and that takes place on such a dam sample. I've also put the equation, but I want to explain the methodology because I don't have results yet, but it's ongoing, and it is to validate this conclusion of very high fracture toughness for plate-like microstructure steels, but on thin sheets this time. Alright, here's a slide of the methodology and the objectives, and it's also kind of an outline of the rest of the presentation. I'll begin with plasticity, the methodology that we used to model it, and some quick results, numerical and experimental. A good understanding of plasticity is prerequisite for damage. I'll also show how we modeled it. And finally, fracture toughness. I haven't got any other results than the one I have shown, but it's to show where we're going. And all this will serve the ultimate goals that are to understand the mechanisms leading to a high fracture toughness, to develop materials with a high fracture toughness, and finally, coupling all the models, optimize the microstructure, taking into account strength, ductility, and fracture toughness. Let's start with plasticity. For the modeling of it, we used 3D finite element calculations on periodic unit cells. Finite elements were chosen because we wanted to have the effect on the local fields due to the presence of an inclusion of a particular shape in a particular direction. And the axis of the local fields is also important for the modeling of damage, as I explain very briefly a bit later. Each unit cell is a ferrite matrix containing an inclusion of martensite. And what changes from cell to cell is the orientation of loading, the loading being always tensile. And the different orientations are necessary because the real material is mechanically isotropic, the inclusions are randomly oriented. And this is why, to get a global response of the material, an average is made on the responses of each orientation. A more general average is also possible on other parameters, since orientation is not at all the only heterogeneity in the microstructure. And those parameters are Martin-side volume fraction, Martin-side carbon content, and morphology that we changed through the aspect ratio. We took oblate ellipsoids for the case of platelets. We took spheres compared to the equax case, and two values of proteate ellipsoids. Here are results of this parametric study. Experimental curves in blue and predicted flow curves in red that are superimposed to show how close we are from reality. It is for the experimental curves for two fibrous, or rather plate-like microstructure steels, and that's why I took an aspect ratio of 0.2 for the computed curves. It is each time for a certain amount of Martin-side volume fraction and carbon content, namely 20% of Martin-side and 0.30% of carbon for the first graph, and 30% of Martin-side, 0.15 of carbon for the second graph. The correspondence is not bad, but there still is a little gap here. It can be explained by two reasons that we already know. Firstly, for the first graph, the experimentally the Martin-side volume fraction is a bit lower than 20%, that's why the economic curve is under, and here it's a bit above 30%, while Martin-side volume fraction has a great impact on the elastoplastic behavior. The second reason is that there's no stage 4 included. We use a Swift type plot for the ferrite that keeps on increasing. That's why the predicted curves keep on increasing, whereas the experimental curves reach kind of a plateau. This is another result of the study. It's the uniform deformation epsilon using the concentric criterion as a function of Martin-side volume fraction. For two aspect ratios, the black curve is for spheres, and the pinkish curve is for platelets. At low Martin-side volume fractions, we overestimate the uniform deformation, and again, it's because of the lack of a stage 4 that I'm integrating in my calculations now actually. Anyway, the trends are certainly correct. For example, that epsilon decreases with Martin-side volume fraction. But the main message I wanted to deliver with this graph is that morphology only has a minor impact, so a little bit between platelets and the aspect ratio, on the elastoplastic behavior. It's also true for proteate ellipsoids or the elastic behavior. We expect a much higher effect on damage and fracture toughness of the morphology. Alright, let's switch now to damage. It is directly linked to the unit cell calculations, because even if not coupled, we use the results of the plasticity calculations as an input for the modeling of damage, for which we use a cellular automated approach. The power of a cellular automaton is that it makes it possible to account for the statistical aspects related to the different possible heterogeneities of the microstructure. And those heterogeneities in the model are the parameters of the plasticity calculations, so morphology, orientation, Martin-side volume fraction, and Martin-side carbon content. The model is based on a limited number of simple equations. It's the attainment of a critical stress for nucleation, or actually it's a distribution of stresses, a Weibull law, another heterogeneity. It's Rice and Tracy for the growth, and Brown and Henry for the coalescence of the voids. This model actually has been developed for luminums by Florana, who's a colleague in the room, and it has been up to now using only decohesion for nucleation. You see the green dots here always appear at the interface. And this choice is justified by the fact that at low Martin-side volume fractions, it's always decohesion that is observed, like you can see on those some micrographs at two different magnifications. At higher volume fraction of Martin-side, particle breaking occurs. Then it's possible to tune the model by incorporating another Weibull law for particle breaking. It will be done. Here are experimental results for damage. It's the graph of the fracture strain epsilon f as a function of Martin-side volume fraction, and it shows the trend that the fracture strain decreases with a higher Martin-side Martin-side volume fraction, and also with a higher Martin-side carbon content. Those trends are already captured by the cellular automated model, but I didn't put the results because it's not quantitative yet. The model runs since recently, so I'm working on it. I don't have These are results of orientation morphology, but it will be for soon. I just wanted to show the methodology, the approach that we follow for taking into account the different heterogeneities. Alright, to conclude, I am working on dual phase steels with a plate-like microstructure, because we have seen that we can really boost the fracture toughness by modifying the shape of the martenstein inclusions, here are platelets. I modeled the plasticity of the steels using finite element calculations, and the big conclusion was that morphology only has a minor impact on the elastoplastic behavior. The model works quite well already, but for an even better match, we are adding a stage 4. And we also worked on the development of the cellular automated approach for damage. The model runs, I didn't show any results, so obviously the perspectives for damage are to compute those results and try to make the model predictive. That's all I've got for today, so thank you for your attention.
Thank you.